Hello again, astronauts. Today, I am here with Ann Isaacs. Ann Isaacs is a graduate student studying astronomy at the Minnesota Institute for Astrophysics. She is an observational astronomer focused on optical wavelengths, most interested in high-energy astrophysics and astronomical transients, as well as cosmology and large-scale universal structure. Hi, Ann. Thank you so much for joining us.
Hi, thanks for having me.
A few questions about your research. First of all, what are transients?
A transient is any astronomical event that comes and goes on what we would call a human timescale. So days, weeks, months, things like that, as opposed to most astronomical phenomena, which take place on the course of, millions, if not billions of years.
So, like a star's entire life is on more of a astronomical time scale, but just a supernova explosion would be more on that human time scale. So that would be a transient.
Yeah, like a star, our star, the sun, is 5 billion years old. So that is, far beyond human conception. Yeah, supernova or other sort of thing that's just there and gone over usually less than a year, something we can see change in front of our eyes.
Cool. So I did some Googling about types of transients because I like to be mildly prepared for these. I don't always succeed, but we're going to try. I ran into novae, supernovae, kilonovae, hypernovae, all as types of transients. So I guess my question is, what is the difference between a nova, a supernova, and the others?
So the word nova is Latin for new, so it literally just means a new star, which is why they're all grouped together, even though some of them are different phenomena. A supernova, which is what I study, there's two types. There's a core collapse supernova, which is a star explodes when it dies. A type 1a supernova is called a thermonuclear supernova, very dramatic, and that is when a white dwarf, which is the remains of a less massive star, gets so much mass squished into such a small place that it also goes crazy and explodes. Then a nova is sort of a less dramatic version of a type 1a supernova, where a white dwarf gets some mass on it, but not quite enough to really lose its mind. So it just explodes like a little bit. I actually detected one of those. It was the very first paper I ever published. Then a hypernova is just a hardcore supernova. So that's a very massive star that's going to collapse. It's related to a collapsar. There's a lot of names for these things. A massive star is dying and there's jets involved. So, stuff is shooting off at crazy speeds. And then a kilonova is actually somewhat different from the other three, because the other three are like, okay, dying stars, dead stars. A kilonova is, we have some pretty good evidence for this. It's when two neutron stars collide, and neutron stars are these incredibly dense balls of neutrons that are like, the metaphor I've always heard is a teaspoon weighs as much as the entire Earth. So the density is just insane, and then two of them crash into each other, and it's this huge event. New elements get made, stuff goes everywhere, and all of them would be perceived as a new star, hence nova. And historically, I believe they were described as guest stars in some historical texts, because in the past, people have actually been able to see naked eye supernovae, and all of us supernova astronomers live in hope that one day that will happen again.
So my wife Nova agrees with you. She actually has this pet project that is staring at the star Betelgeuse and willing it to go supernova whenever she can see it in the sky, which isn't often because we live in Chicago, but whenever we're camping or if she's on a plane. Even one time she told me that she was on a plane to go to a conference, and she always gets the window seat. She was looking out and saw Betelgeuse, the star, and just spent like half an hour staring at it, willing it to explode. This was back when Betelgeuse was oscillating a lot, and unfortunately, it's calmed down now. She's very disappointed in that.
Yeah, I was kind of hoping.
Yeah.
Would have
So
been cool.
yeah, you've got many allies in the Betelgeuse should explode already camp. A nova is when a white dwarf is slowly eating another star like a red giant and flares up. It could flare up multiple times because it doesn't destroy itself completely. A type 1a supernova is when a white dwarf is eating likely a red giant and just completely rips itself apart. Like it gets enough mass to just completely explode.
It reaches a certain mass limit defined by quantum mechanics where it's just like, nope, can't be any bigger. Yeah. I'm done.
A hypernova is more like the core collapse supernova, but just way, way bigger, badder. We can make it better than before. It's the $6 million supernova.
It's also got jets, which is when just stuff gets sort of targeted along a very specific straight line and gets accelerated like crazy to like, high fractions of the speed of light.
So supernova, now bigger with more features.
Yes.
Get excited for the sequel. And kilonova was when two neutron stars, and neutron stars are the remnants of core collapse supernovas. Mm-hmm. So it's also the sequel to supernovas, but more like the closer of the trilogy, because it's two former supernovae, now neutron stars, colliding in just one final burst. Does that usually lead to a black hole or no?
I believe it does, but more broadly speaking, we're more interested in the fact that it creates a lot of new elements, like heavy elements that we were not really sure where they came from. So anything heavier than iron has to be made somewhere other than the heart of a star. And we're pretty sure kilonovae makes some of that stuff, which is very cool. That's one mystery we're starting to track down.
Yay! So there are other types of transients that I looked up. If you wonder, did Astra just look up list of transients 5 minutes before the interview? Yes, that's exactly what I did. What are variable star variations?
Well, there's a couple different ways I could answer this. A variable star like Cepheids and RR Lyrae are the most common. And that is a star that has a very predictable pattern of variation. It sort of pulses, and it makes like a little curve like that. So if you watched it for a long time, it would be brighter and dimmer and brighter and dimmer in a very regular, predictable way. We actually use them to measure distances, which is interesting because how long it takes to vary is directly related to how bright they are. And so I don't know all of the stellar physics involved, but basically it gets really bright and then it gets so kind of puffed out that gravity pulls it back in, it contracts on itself, and then the gravity pulling it back in makes it very hot and it expands again, so it pulses. But stars also occasionally flare in other ways, so this is most relevant for our sun because we live next door to it, but it can do things like flare or, just shoot a ton of its own material out in a coronal mass ejection. We think we could see these for other stars. I met somebody at American Astronomical Society who is hoping to study exoplanet atmospheres by looking at the interaction of a stellar flare with the atmosphere. That's how we get the aurora. So yeah, we can get both regular sort of pulsing ones and also just stars occasionally get mad and spit out a bunch of material or a bunch of other particles. That's not something we can see as far away as we can see regular variable stars, but it is still pretty interesting, especially because we live next to the sun and we like to understand things that happen with it.
Yeah, let's not have another Carrington event, please. I'd be very okay if we just didn't.
Yeah, I was talking about that with the solar flare person. She's like, yeah, the thing is, for me to observe an event, it might have to be up to 10 times more intense than the Carrington event on another star. And I was like, you know what? I think I'm glad we don't live there.
Yeah, yeah, very glad. So I just want to clarify for our viewers, variable stars do pulse, and they expand and then contract as pressure and gravity, the two forces that kind of determine a star's size, fight. But they are different than pulsars. They pulse, but they're different than pulsars. Pulsars you can kind of think of like lighthouses, maybe.
That's the metaphor I use in pretty much all the outreach I do.
Yeah, so pulsars change because they are rotating. So a pulsar is kind of like a lighthouse. It rotates, and it's basically a neutron star that has jets going kind of up and down. But and it rotates. But it's not always perfectly aligned like this to us. Sometimes it can be tilted. So as it goes around, think of my thumb as the jet. We see more and less of the jet as it rotates. So think of the jet like a beam of light in a lighthouse. That's what a pulsar is. The neutron star that is a pulsar isn't actually changing, it's just rotating, whereas a variable star is actually getting bigger and smaller. Did I do okay?
Yeah, I'm actually wearing my pulsar shirt.
Nice. So are pulsars transients?
We used to sort of consider them that way, but I would say they're not because they're staying put. Broadly speaking, the pulsar system on the shirt I'm wearing actually is not exactly the same, and it was the first indirect evidence of gravitational waves, which is super cool, but I won't get into now. But I would say we don't really consider pulsars to be transients because the object itself, as you said, isn't really changing. The neutron star is just spinning. It's not actually changing in dramatic ways. And we know now, we didn't know when we first discovered them, which is why we called them pulsars, because we didn't know they were rotating. We thought they were just going on and off. Basically, if you know where a pulsar is, you can just look over there and you'll always see it again. They're so reliable that people have proposed using them as like an outer space GPS sort of deal. So yeah, I think because they are so regular and known, we wouldn't consider them transients. Of course, I don't know if other people have different opinions on that. I would not consider them transients.
What are gamma ray bursts and fast radio bursts?
Well, the fun thing about these is that they're the two that we probably know the least about. So gamma ray bursts were discovered in the 60s or 70s during the Cold War by accident, and they were on classified satellites, so nobody even knew about them for another decade or two. It's a very funny story. It is what it sounds like. From deep space, way far away, there's a burst of gamma rays. The amount of energy we get from them is comparable to a supernova or other really bright event. They're some of the brightest events we can see, and we're seeing them from other galaxies. Actually, as we observed more and learned about them, they sort of fall into two categories, short and long. The short ones we're pretty sure are associated with kilinovae, and the long ones we think are associated with certain types of supernovae. And we've been able to find, some evidence, but we haven't built up enough of a population to be like, this is what causes that. I say it's very likely, but we don't know for sure. Fast radio bursts we know even less about because they were only discovered in like the 2000s. I actually went to a talk with one of the scientists who first discovered them, and this was when I was in college, so I want to say 5 years ago, maybe 6. She said the great thing about fast radio bursts is that no matter what theory you have, no one can tell you you're wrong because we don't know yet. So they're, again, very fast pulses of radio waves that come from space, very short amount of time. What's interesting about them is when you look at them, it's very clear from the way they show up when you take your pictures that they're coming from outside the galaxy. And so that was also pretty cool because, again, that means they must be pretty bright. Yeah, we don't have a great sense of what causes them. I believe kilinovae and other transients are possible candidates, but we're still learning a lot about them. One recently was discovered in the Milky Way galaxy, which I'm a little jealous of because the fast radio burst people found their thing, and then like a decade later they found one in the Milky Way. And us supernova people have been waiting for a supernova in the Milky Way for like 50 years, longer. Anyways,
It's
they found
okay. Nova and I are on board. Team Betelgeuse explodes.
yeah. So they found a fast radio burst that they could match up with what's called a magnetar, which is like a pulsar, except its magnetic field is just gigantic, like millions of Teslas. I don't know if that's a useful measurement. The strongest magnet we have on Earth is probably about somewhere between 4 and 8 Teslas. These are, and that's like, the magnet where if you hold it too close to a lamppost, it'll rip your arm off. These are neutron stars with a field 1,000,000 or even 1,000,000,000 times that. And they're really bright, and occasionally they flare. And we saw one flare, and we caught a fast radio burst. And it was kind of on the dim side, but that's pretty promising evidence for magnetar flares being one possible source of fast radio bursts.
All I'm getting is that I'm just really glad I'm not in the vicinity of either of those two.
Yes, broadly speaking, a gamma ray burst would probably be worse because gamma rays are very bad for you. That's what the lead is there for.
I am definitely against me getting all the cancer.
Yeah. This is one of those things that people ask you a lot when you're an astronomer is like, well, if a gamma ray burst or a fast radio burst happened really close to Earth, wouldn't it kill all of us? And it's like, I mean, probably. Not that likely though, and we try not to worry about it because also like there is nothing we could do about it.
Yeah, it's much more interesting to be worried about another Carrington because that would cause significant issues, but we could plan for it. Whereas gamma ray burst or fast radio burst would probably all just be very, very dead.
I personally do not know of any star or object close enough to us that would cause such an event. So I try not to worry about it.
I also try not to worry about things I have no control over, but I fail. Moving on to active galactic nuclei, it turns out that a changing active galactic nucleus can be a type of transient. Can AGN evolve that quickly?
Yeah, absolutely. We don't usually AGN people and transient people don't like share a poster session or talk to each other all that much, but AGN, active galactic nuclei, are powered by the black holes at the centers of galaxies eating, and they can absolutely flare on scales of days to weeks. So sometimes an active galactic nucleus will gobble. We assume it's eating something big. I studied this briefly, so I know a little bit about it. An active galactic nucleus can gobble something up, flare real bright, go back down. Some of them flare a lot quicker than others. It's some pretty interesting stuff.
So moving on to transit types that can help detect exoplanets, because I, for one, can't get enough of exoplanets. I think they're just the most interesting thing and don't get an outsized amount of attention at all. I love them so much. And
about to say, you and everybody else.
There are two types of transients that can help detect an exoplanet. The main one is transits, a star that we can see and an exoplanet passing in front of its star, or really any object in space passing in front of another object and blocking its light. So we might not be able to see the planet, but we can see the star's brightness dip a little bit. And that dip in brightness occurring multiple times over a regular period is how we can detect the presence of exoplanets, even if we can't see them. So gravitational microlensing is a lot like transit. It's like a transit in that we can't see the moving object, just its effect on the light from the further object. But instead of a planet passing in front of its host star and we see a dimming effect on the star, in this case, we actually see a brightening of the distant star because of the way the gravity from the nearer object bends the light from the much further object usually magnifying and distorting it. Both transits and gravitational lensing involve us getting very, very lucky because there has to be a chance alignment. Either the planet has to pass through, either the exoplanet, because technically exoplanets aren't planets, at me, IAU. Technically, an exoplanet has to pass in front of its star to us. So if it's orbiting this way, we won't see it. And a gravitational microlensing event only happens when an object passes almost directly in front of another object. And if it's perfectly aligned, the further object kind of forms a ring around the closer object. We call that an Einstein ring because it is an effect of general relativity. If you want to learn more about general relativity, we do have a video about general relativity.
One cool thing you can do is go on Zooniverse and be part of a citizen science project of looking at these light curves. So it's basically they take a measurement at every point and then suddenly goes down, then it goes back up, another bunch of points. And so I've looked at a couple of those with my students and been like, yep, that's an exoplanet.
And gravitational microlensing, while it is used to find exoplanets, it can also be used for surveys to try to find dark matter machos, which are not to be confused with dark matter WIMPs. Dark matter machos are potential high mass sources of dark matter, and WIMPs are low mass sources. So dark matter is either caused by relatively few machos or a whole bunch of little WIMPs, or a combination. We're not really sure. It's dark. We can't see it. Or axions or something else. There are apparently a bajillion particles, shouts Nova from the other room.
There are a lot of possibilities for dark matter. I believe machos are currently slightly disfavored and people prefer WIMPs, but yeah, the idea that you could catch a microlensing event, basically a bright object passes behind something we can't see, and in doing so, it just gets all weird. If I'm wearing my glasses, what I like to do is point out that if my prescription is pretty high, if I'm wearing my glasses, you can see further around my face than when I'm not, and lensing is kind of like that. So if there's a dark, heavy object, you can sort of see around it to something we wouldn't normally be able to see, which would be pretty cool. Unfortunately, as far as I know, we have not detected any yet.
And you mentioned gravitational waves earlier in our conversation. So gravitational waves are ripples in space-time caused by black hole and neutron star mergers. If you want to learn more about gravitational waves, we interviewed Dr. Maya Fischbach. That was actually our first scientist interview, was about gravitational waves.
We have a big multi-messenger astronomy program within Minnesota Institute for Astrophysics. Multi-messenger astronomy is anything where you're looking at photons, light, as well as particles from space, so neutrinos or cosmic rays, and including gravitational waves. So I actually have a couple friends in the department in my year who are working on LIGO gravitational wave detections. I think this stuff is really cool. I would definitely like to be involved with it. The LIGO detection they were able to localize, correlate with a gamma ray burst was incredibly cool. Multi-messenger astronomy is hot right now, and as we get more gamma ray events, as we build better detectors, I think it's going to become more relevant to what I do.
How do observers find transients? Do you just kind of hope that one shows up when you're pointing a telescope at it?
I mean, that's genuinely the old way. I really recommend Bill Bryson's A Brief History of Nearly Everything. It's a great book, and he talks about a dude, who just lived in Kansas and would just look at the sky every night, be like, hey, that star wasn't there last night. And that's how we found supernovae for years upon years. More recent modern methods, so Palomar Transient Facility and Zwicky Transient Facility, among others. Basically, they take pictures of the night sky, entire sky, every 2 or 3 nights. And they take an old image and they subtract from it the new image. And anything that's new will pop up real bright because it wasn't there before. And they have computers that detect those sorts of things, and then they send alerts out to the astronomical community, and anybody who's on a telescope and cares can go and point their telescope at that object. So now we do it with computers, which is incredibly useful. Other projects that use this method are Assassin. I
That's a
don't
great
remember.
project name, by the
It
way.
really is. I don't remember what it stands for, but it's ASASSN, and the SN is supernova. I would say that's probably the most common modern detection method because there are a lot of transients, and as the night sky changes, and we just let a computer say, "Hey, that wasn't there before." That's a 1987A, which is one of the most famous supernovae because it happened in the Large Magellanic Cloud, which is really close by. At least according to one book I read, they're pretty sure the first detection was made by a dude who went outside to take a break from telescope time, looked up at the Large Magellanic Cloud, and said, I've been studying that thing for a while now, and I'm pretty sure that star is new. And later, many other facilities noticed this, and about people said, "Hey, wait a minute, my photographic plates have changed," because when we use photographic plates, but the first detection was just a guy being like, "Hey, wait a minute." So, and that was, 1987A, we didn't have ZTF and PTF and all those, but it's still a lot more recent than you'd necessarily think.
Yeah. I really like that our technique has gone from person looks up and is like, hey, that's new, to computer scans the whole sky and then says, hey, that's new.
Yeah, basically.
Yeah.
Um,
Hey, if it ain't broke, don't fix it.
yeah.
So when we get a transient that we want to look at, do we always know what type of transient it is based on the signal? Like if it's emitting in this wavelength, is it definitely this? Like I guess for gamma ray bursts and radio bursts, like they're characterized by the observation. But do we always know when something is a supernova versus a hypernova versus a nova versus a kilonova, all those things?
Definitely not. So gamma ray bursts, even we have like they're falling into two categories, short and long, and we wouldn't know that until later because some of the short ones are on the long side and some of the long ones are on the short side. Same thing is true of FRBs, although the sort of, again, we don't have a huge population of them yet. But the first thing I ever published was an astronomer's telegram, and my advisor said, "Hey, I think you should look at this object in the night sky." So I pointed the telescope at it. I took a spectrum. I went home. I analyzed the spectrum, and I looked at it, and I said, "That's not a supernova." And I emailed it to messaged my boss and said, "Hey, that's not a supernova." And he goes, "You're right, it's not. I really thought it was." And we had to go hunt down someone who knew what it was. So yeah, if there's a new thing and it's optical, what you really want to do is take a spectrum of it. So that's when you pass the light through a prism and see sort of, oh, well, there's a lot of red light, but not a lot of blue light, and that tells you something. Yeah, if you don't have that, you can make guesses, but I think a spectrum is probably the best way we know how to classify these things.
So a spectrum I know can tell you what elements are in the thing because they'll absorb some light, but what else can a spectrum tell you?
For me, the key thing would be the temperature. You're talking about absorption lines. We can also see emission lines, which are basically the inverse of absorption lines. What most spectra have an underlying continuum. A lot of times it's what's called a black body, which means it's basically emitting because of how hot it is. And so you'll see a specific pattern, a very specific curve, and from that you can figure out how hot the object is. And in fact, how hot it is will affect what emission lines you can see, the temperature of the object, and also you can get continuum from other sources that aren't just it being hot. And things like synchrotron, which means that there's a lot of magnetic fields going on, Bremsstrahlung, which is German for breaking radiation and just means there's a lot of free electrons floating around, all sorts of interesting things like that. So the spectrum tells us what it's made of, but also like how is this light being produced? So what processes are underlying it, which tells us a lot about the physics of the event. How hot is this object? Because, a very big bright star might be very hot, but other things maybe not so much. Although, of course, compared to even this heat wave we're living in, space and stars and stuff are pretty hot. And even if there's a lack of continuum, that tells you something else because it means that there really isn't much going on besides these elements just sort of chilling out in space.
So you talked about the first paper you ever published. What is your current research project? What are you currently working on?
Right now, I'm studying the host galaxies of type 1a supernovae. So these are supernovae that happened a while ago and they faded away. And I'm looking at the galaxy they happened in. And the question I'm asking is basically, does the galaxy impact the supernova in any way? The main thing I'm looking at right now is H alpha, which is a good proxy for star formation. So basically star formation rate. And I'm saying, okay, if there's a lot of star formation, does that impact the way a supernova happens? And if I do see that, why would that be? So this is all in service of further understanding the expansion of the universe, because we use type 1a supernovae to understand how the universe is expanding because, well, we used to think they all happened exactly the same way. And now we know they don't happen all quite exactly the same way, and we're trying to figure out some of why. We've been able to, figure out a few things, but some of the others are still a little mysterious. So what I'm doing is I'm saying, okay, if the galaxy has a lot of star formation going on, is that impacting it? And is that impacting how the supernova happens? And then is that impacting our understanding of the expansion of the universe? Because it very well could. So hopefully I will have some results in late fall. The most common effect that's cited is something called the mass step. Supernovae in large galaxies tend to happen a little differently than supernovae in small galaxies. Nobody knows why that is. It's definitely a thing, but no one seems to know why. Multiple papers see it, and the theorists are sort of like, don't know that one yet. So my work is hopefully going to look a little more into that. And because of the resolution of the data I have, I can actually look at like where the supernova happened in the galaxy and say, okay, well, yeah, there was star formation going on over there, but right over here, there wasn't for this supernova. And that can be pretty relevant. And this is useful because while supernovae, come and go, the galaxy is pretty much the same as it was, 20 years ago when the supernova happened. It's pretty exciting. At least I think it's very exciting.
That's really exciting.
Yeah. So fingers crossed. I'm probably not going to solve the problem of we don't really know what the Hubble constant is, but maybe I can make some progress.
That's what science is. It's making a little bit of progress towards the big questions. And if we all work really, really hard, we'll all make a little bit of progress. And then the scientists who come after us will make even more progress. And eventually someone will find something close to the answer. We'll probably never get like the ultimate answer, which is good job security. Science will never be over.
Whenever they think physics is over, they're wrong. It's happened a couple of times.
There were people who thought physics was over when the steady state model was still a thing. So,
oh yeah, everyone's like, oh, the physics is over, and then they discover, quantum mechanics. Not so much.
Yeah, less over. Once someone figures out like the graviton, or once someone figures out gravity, then maybe I'll hear an argument for physics being over. But until that happens, we don't even know how stuff works now, let alone how the beginning of the universe happened. So
yeah, I'd also like to hear, somebody successfully unite quantum mechanics and general relativity. It's sort of like, yeah, if you do that, first of all, you'll be the most famous scientist ever. Second of all, maybe then I'll accept physics is approaching done a little bit.
Yeah, maybe.
And now it's time for Gambling with Eris.
My wife, Nova, studies high energy astrophysics as well and has done some work with transients. So I thought I'd have the two of you help Eris win a few bets. I have a list of transients going head to head, and because Eris has a gambling problem.
Hello, it's Eris, writer for Bad Astra, and apparently someone with a gambling problem. Astra, it's not a problem. I can control it. I have perfect control. I can stop whenever I want. I can.
She's going to bet on which one will evolve on a shorter time scale. So this isn't going to be about which one has a faster velocity, but which one has a shorter time that we see it changing. You and Nova will have to help Eris pick the fastest horse. Now, unfortunately, Nova told me that she couldn't be here today because she is in Italy at a conference, but she gave Cece a copy of her notes. So Cece will be contributing for Nova. She will be speaking with Nova's voice, but Nova is currently in Italy and didn't want to call into a Zoom call in the middle of the night. Anne, are you ready?
I'm ready.
Cece, are you ready?
Yes.
Okay. Are you sure you're ready, Cece?
Extremely.
Cece, Nova left you phonetic pronunciation notes. How do you pronounce that Nova right there?
Eris Ophiuchi.
Okay, Ophiuchi. R.S. Ophiuchi. Are you sure that's how it's pronounced?
Nope.
Have you just been pronouncing it that way because Nova does?
Yep.
Okay. So our first match pits R.S. Ophiuchi Nova versus Tycho Supernova. Specifically, we are going to look at how long R.S. Ophiuchi takes to drop to about 2 magnitudes below its peak versus when Tycho Supernova dropped to no longer visible to the human eye. So do you think it took R.S. Ophiuchi less or more time to drop about 2 magnitudes, or for Tycho Supernova to no longer be visible to the human eye? Which do you think happened faster? Cece and Anne, what are your thoughts?
My first thought is that I believe novas are generally faster, and in fact, I just read an article from AAS about American Astronomical Society conference about the fastest nova ever, which rose and faded in just one day. I would say broadly speaking, novae are faster than supernovae, but I don't know about these particular ones.
Okay, Cece, what did Nova say in her notes about novae versus supernovae?
I would also say that the nova is likely going to be faster because RS Ophiuchi specifically wasn't so fast that it evolved over one day, but over 5 to 10 days, it significantly faded from view. So probably the nova.
Okay, so Eris, what do you think it's going to be? Cece and Anne both say the nova, although Cece is using Nova's notes, so they might be a little biased.
Tycho and supernovae I've heard of, and that was like my initial gut instinct, but it seems that both Cece reading off Nova's notes and Anne both say that the regular nova, however it's pronounced, would be the faster of the two. So I am going to trust the experts here and say that the nova is faster.
Anne and Nova were both very correct. Yes, Cece, you got it right. Yes. Oh, yes, you're celebrating getting it right. Okay, that's my brain.
Yes. I got it right. Ha!
Okay, so yes. Okay, that's excessive celebration. I'm going to have to penalize you 5 yards. Don't make me make it 15. R.S. Ophiuchi rises steeply and rapidly to a maximum and then quickly declines, dropping about 2 magnitudes over a week. So 5 to 10 days was correct from Nova's notes. Yes. Tycho supernova, when it first appeared in November 1572, it was as bright as Venus and could be seen in the daytime. And it took over the next 2 years to dim and no longer be seen with the naked eye. So yeah, it was a week versus 2 years, and the nova was much faster. So good job, Cece, and good job, Anne. You gave Eris correct information.
You see, what happens when you listen to the experts is that sometimes when you parrot the same answer, you are correct. As someone who has never studied astrophysics, I took one astronomy course in college.
And it's a good thing Eris took it, because She bet Cleo on it.
Yeah, I'm a genius.
Okay, so next up for Cece and Anne is the Lorimer burst, which was a fast radio burst, versus GRB 020813, so 2813, a gamma ray burst. Which do you think evolved faster or faded faster?
Is this a short gamma ray burst or a long gamma ray burst is my first question.
It was a long gamma ray burst.
Well, in that case, I'm going to go ahead and say the FRB was probably quicker. Long gamma ray bursts are usually longer than about a minute. That's what I did my senior thesis on, so I certainly hope that's correct. And fast radio bursts, as I remember, are usually much shorter than that.
Okay, Cece, did Nova leave you any notes on that?
Given that this is a long gamma ray burst, I'm also going to say that the fast radio burst is going to evolve on a shorter time scale. I can't quite remember what the time scales of either of those are because I don't study them, but fast radio bursts, I think, are seconds to minutes tops.
Eris, what do you think?
Okay, so again, I feel like I have to listen to the scientists because they are both in agreement that the radio wave is going to be the one that dissipates faster. And speaking as someone who kind of knows about sound, well, at least light and like light rays, yeah, gamma rays have more energy, so they have a shorter wavelength, whereas the radio ones are drawn out over time. But since it was a long gamma ray burst, since it was clarified that it's a long gamma ray burst, we're gonna go with the radio thing. It is incredible to me how I can listen to the whole question, the conversation, and they will use the actual names, and it just loses my mind. Just gone. It's gone. But yes, final answer, radio waves.
The good or bad news, I'm not sure which because we filmed this before I asked Eris for her bets, is that Cece or Nova and Anne were both correct.
That means I'm correct, and that's all that matters to me.
Do you want to celebrate again being correct? Yes. Yes, you were correct. Good job. Yes, you did such a good job reading Nova's. No, oh God, that was my brain.
I didn't lose this one. Thank you. Put it on notes.
The Lorimer burst was actually less than 5 milliseconds in duration. So Cece, Nova was actually a little bit long in her.
I was very off on that.
Yep, but you're still celebrating. And you were completely correct in terms of the length of long gamma ray bursts. You said they were on the order of a bit over a minute. So GRB 020813 lasted around 125 seconds, so just over 2 minutes. So great job. You two know your FRBs and GRBs. Next up, we have OGLE 2003 BLG 235L, which was the first detection of a planet by gravitational microlensing, versus the orbital period of Kepler 22b, an exoplanet detected by its transit, also featured in a show I like, Raised by Wolves. The microlensing isn't the planet lensing its star. It's the planet and host star both going in front of a more distant object, like a star or a galaxy, and both of those lensing the distant object in turn. So the question here is, for the microlensing event, how long did it take for the close thing to pass by the far thing? And for Kepler 22b, the transit, we are asking about the full orbit of the planet around its host star, not just the amount of time it took for one transit, because to detect that it's actually there, you have to see it go by twice. Does that make sense? Cece, is that a fair comparison, because we're trying to center observation in these questions, not the astronomical objects themselves. We're kind of, how long does it take for us to detect it was kind of was the metric I was using. So Anne, which do you think is fastest?
Broadly speaking, planets discovered by the transiting method tend to have very short orbital periods because, like you said, we have to see them pass in front of their star 2 or 3 times. So it has to, so generally speaking, these planets have pretty short orbital periods. They'll be, pretty close by their host stars. Those two things are directly related. This is hard. This is quite difficult because, a lensing event would only be the amount of time that the host star and exoplanet are just at the right alignment, which may not be very long.
Yeah, it's the difference between just at the right alignment and far enough away that you can figure out what the front object was.
I don't actually know if microlens planets are more likely to be close or far from their host stars, especially because, as I understand it, microlensing is relatively uncommon as a way to detect exoplanets.
It's mostly that the planets have to be giant, like very big relative to their star in mass.
Definitely. I would tentatively say I think the microlensing would be a little bit shorter, but I think they're probably, it's very hard to say because exoplanets have such a wide variety in their periods, and because I don't know much about microlensing for detecting exoplanets.
Well, Cece, you cannot avoid the question. I know Nova left her notes on this. So what did Nova say?
Nova doesn't know either.
Is that why you were trying to avoid the question?
Yep.
I think I may have made this question a little too hard.
Because now this depends on the relative velocities of the planetary system and the lens.
Yes.
Yeah, this is getting a lot into areas I don't specialize in or study.
Cece's not sure. Anne is not sure. Okay, over to you, Eris.
Okay, so it's, you got the exoplanet that was discovered by microlensing by being in front of the star at the right time versus Kepler that had a transit that we did observe by more traditional methods. And neither of the scientists are helping me on this because they both don't know. So, I don't know what the first planet is. Or technically not a planet because exoplanets aren't planets either. Justice for exoplanets too. I think I'm gonna go with my gut, and my gut says I've eaten a lot of pizza. So my brain says Kepler, based on the based on whatever fallacy it is, where you assume the thing that you know about already is the correct answer. The one that familiarity. I don't know. Either way, final answer is going to be Kepler. Let's see if I got it right.
Lucky for you, Eris, you guessed correctly.
Hell yes.
The microlensing event that I mentioned, OGLE 2003 BLG 235L, was discovered in 2004, and it wasn't until 2006 that the closer star had passed far enough from the background source to discern the light separately. That microlensing is either 2 or 4 years, depending on how you count it. Kepler 22b, both Cece/Nova and Anne were correct, because Kepler 22b has an orbital period of around 290 days. So it is a very, very short orbital period.
I did get this correct. It is Kepler. Thank goodness I am familiar with that name of that exoplanet, because otherwise I don't think I would have been able to tell the difference.
It was used for the show Raised by Wolves because it is thought to be an Earth-like planet. Scientists have gotten pretty excited about it. but I actually chose this question because I thought it would be very difficult.
Also, Nova did not get it correct. She chickened out and did not answer.
Wow, Cece, way to throw your mom under the bus.
Always go for consistency over a miracle, I guess.
I think you might have a licking problem.
So I have been correct every single time, and nothing can convince me that I will lose any money on this. So is it a gambling problem or a gambling talent?
Last head to head, which felt longer? From an observer's perspective, not an actual timeline. The JWST design and construction, which started in 1996 and was just completed in 2021 December, when JWST was launched, or the Trump presidency, which objectively was only 4 years long, but which felt longer. Remember, these aren't absolute velocities. They are how we observed them.
Okay, last one, super easy. What felt longer versus Trump presidency versus the James Webb Telescope? I'm pretty sure that's what that acronym is. James Webb? John? James? Something with it. J-Webb. J-Webb Telescope. I write professionally for a science YouTube channel, and I cannot remember what the acronym is for the really big fancy telescope that everyone was really excited about. But in terms of time period of the first construction for the telescope versus when it actually got finished in 2021 versus the Trump presidency, that was 4 years, I am going to say 100% the Trump presidency was longer, mainly because I didn't know how long it took for the James Webb Telescope to actually happen. I know it was before the pandemic. I knew it was on the radar, but I figured out the telescope was done when it was done. So, yeah, of course the Trump presidency felt longer. I don't even need to consult the experts on this one. I do not like it.
I mean, I would say probably the Trump presidency felt longer because I was not involved in the astronomical community in college, not until at least partway through college. It's possible also, the anticipation for JWST, it kept getting put off to the point where we were sort of like, yeah, whatever, it'll happen eventually. And also we were excited for JWST to get here. And so it was sort of one of these like, oh, it's very exciting. We're looking forward to it. And I guess we were also looking forward to the end of the Trump presidency. Since we were living through the consequences of it, to me personally, it definitely dragged a little more.
So, Cece, I know that you were born in December 2020, and moms didn't even take you home until Joe Biden was already president. But you have Nova's notes. So what does Nova say about this?
Trump presidency, 100%. Although, based on the way that I am starting to close my eyes, this interview is a good contender.
Eris?
Now that I've listened to the answers, this raises more of a philosophical question because how can you determine who is right or wrong in this situation? You're basically betting that somebody else will have the same perception as you. If we look at time as an objective fact, like the measurements that we make time in as human beings, then the correct answer is going to be the James Webb Telescope felt longer because it was objectively speaking longer in terms of the timeline. And the James Webb Telescope is insulated to a very specific community, but objectively on the timeline that's much longer, even though fewer people perceived it.
I mean, JWST, James Webb Space Telescope, obviously very exciting as a telescope. It first proposed in the 90s. Yeah, that one took a while, and the launch date kept getting pushed back. The first proposed launch date, they were like, oh yeah, we're going to have it up by 2010. I don't know if it was that early, and they just kept pushing it back and pushing it back every time they approached the deadline. There's a comic on XKCD that was saying, well, at least the slope is less than 1. Eventually we were waiting for a long time, and especially as it got closer, they say, okay, it's the 22nd, and they said like October, it's going to launch on Halloween. Okay, it's October, and actually December 22nd. Okay, and then I said December 24th. Okay, and then finally it was on Christmas Day, and I woke up at 6 a.m. to watch that, and if you know me, you know that that is not a natural time for me to be awake. I watched that launch, and I learned a new French vocab word, nominal, and watching it launch, and then it was really amazing, you know, watching it launch and seeing all that footage, and then waiting the 30 days for it to get to the Lagrange point, and then waiting for all of the commissioning. Yes, there has been a lot of waiting, and I feel like as we got closer to the end, it got like the anticipation got more intense and more real, because we're like, wait a minute, this is actually going to happen soon. And for a lot of the people I know, it's sort of, it is probably going to be to define one of the defining instruments of our careers. So the stuff we've seen already is just so gorgeous.
And now that everything has gone well, like everything's deployed, it's at the Lagrange point, nothing broke, I think we can kind of look back and admit just how stressful it all was, because hundreds of points of failure where if any of those went wrong, we would have no way to fix JWST because it's all the way out at the Lagrange point. When we first launched Hubble, it didn't work properly. We had to go up and fix it, but it was just in orbit. So going up to service it and fix it was doable. That's not doable for JWST. And it was 10 times over budget, took more than 10 years longer than it was supposed to take. Like, the project started in 1996. It's been going for 26 years now. And if it went wrong, like, not only are tons of young astronomer careers just kind of dead in the water because they put in their postdoc that they would be using JWST data for everything, but astronomers as a whole, like, observers aren't getting a new space telescope for the foreseeable future if this doesn't work. Even theoretical astrophysicists have to worry about not getting funded because it would make astronomy as a whole look bad. And that was very scary for a while.
It was really stressful. And especially because astronomy, we really want it to be a collaborative community internationally. At least I want it to be. I think most of us do. So it's sort of like, look, I don't want to be pitting countries against each other for this particular thing, especially as these projects evolve and really become things that you can't do as a single country. So it was very nerve-wracking. And at AAS, they reported that everything is going incredibly well, even exceeding expectations or even exceeding design specifications. So I'm looking forward to that data.
So that's it for me feeding Eris's gambling problem. I should really probably stop enabling her, but I won't, because I value my own entertainment more than her mental health.
Again, it is not a problem if you can stop at any time. I do not have a gambling problem, and considering I got every single one of these correct without even cheating once, it is not a gambling problem, it is a gambling skill. For the last time, Astra, I don't have a problem. You have a problem.
But I'd like to move on to some more personal questions, specifically toward your activism and advocacy. Specifically, I know that you're very involved with WIPA, the Women in Physics and Astronomy organization at Minneapolis. Could you tell me a bit about that?
It's a combination of an activism group and just like a place to be a woman in one of these very male-dominated fields. And it's really important to me that we reach out in these ways, because I think one of the most valuable parts of a science community is that everybody is coming at it from a different angle and a different perspective. And so the more perspectives and like ideas we can bring in, the better. A lot of what we do is just helping people feel comfortable in the department, saying like, this is the space for you to come be a woman, and also, you know, maybe complain a little bit about the sexism you see and you feel, even when it's, you know, very kind of subtle. It's hard to put your finger on it and say, that was a sexist thing someone said to me. So it can be really good to have a place to go and tell someone about this thing, and somebody else can validate you and say, yeah, that was pretty messed up. We also do a lot of outreach work. So we organize panels and events for our incoming students. We host talks of women in astronomy and physics, the Waffles series. And that's where we are showcasing women in astronomy and physics who have done these incredibly cool things. And I think that in that way, you know, having a role model is really valuable. We also do some mentorship, so undergraduates can reach out to us for help. You belong here. And we also make that space to feel like you belong.
Who do you think was robbed more, Cecilia Payne or Jocelyn Bell? Not to pit women against each other.
I just realized Jocelyn Bell is the same as Jocelyn Bell Burnell, who was one of the plenary speakers at AAS this time. So I've actually seen her speak, which was incredibly cool.
She came and spoke at Northwestern when Nova and I were undergrads, and Nova has a picture with her, but I didn't come to that lunch because I had a class at the same time, and I'm still salty that even though I got to see her speak, I couldn't be in the picture.
Historically, obviously, Cecilia Payne probably had it worse just because she was born earlier, and the earlier you are, the worse it is. We don't want to pit women against each other, and while it's great we've made progress, there's still plenty of ways to go.
On the one hand, for me, Cecilia Payne got her results just completely denied by her professor, who just thought there was no way she could be right, likely due to some unconscious bias, not just against women, but against grad students too. But then Jocelyn Bell, her discovery did win the Nobel Prize, but she didn't get it. It went to her advisor, who didn't do the work.
That's also a grad student thing.
Yeah.
I mean, I had a professor in undergrad, great guy, Joel Weisberg, who was part of the discovery of this pulsar and indirect detection of gravitational waves. And he was this close to getting a Nobel Prize, but it can only go to 3 people. So he was right there. He was just number 4 on the list.
Oof.
One step I heard that's, I didn't think about this, but most papers these days are first initial, last name. And apparently that's because people have discovered that, you know, then you don't unconsciously bias yourself by reading either the first name, you know, John or Jane or whatever, and thinking, oh, a woman wrote this, oh, a man wrote this. So I'm hoping that we can sort of push more for that. Like, you get your credit. I would be credited as A.M. Isaacs, but you can avoid some of the bias. That said, last names also can carry a racial bias, and that's a whole other can of worms that I'm not involved in as white people, but it is so vitally important that we reach out to communities of color and say, like, hey, you are also welcome here in astronomy. We can say all we want to fix this problem, but we have to take more concrete steps. Well, final thoughts. For high schoolers who want to study astronomy, I would say, like, try it. It's okay if you don't love it. You know, try it, see if you like it, try a few different things, you know, test out a few different fields too, because maybe you're not really into theory, but you like observation, or vice versa. And also, if you're a high schooler, make sure that you have a broad base of knowledge, because you will want to know astronomy. You will also want to know how to write a good grant proposal. So yeah, as a high schooler student, I would say go for it, try it, learn it, see what you like, you know, learn more about yourself. And I don't want to discourage anybody. I just also feel like, you know, making your career, sometimes there's a lot of pressure to like choose your career when you're 16. It's okay if you change your mind. But if you think you might like astronomy, you should absolutely be, you know, taking any classes you can, just seeing what you like. For undergrads, very similar advice. Make sure you're getting that broad knowledge base, learning how to write and how to communicate, because historically, scientists are not the best at communicating our results. And I think that is a thing we are working on, and we should continue to work on. And again, you need to write a good grant proposal. So, you know, and also once you get into undergrad, you can really get into some subfields. I would really recommend getting into research if you can, just because that will tell you like what kind of work you want to do, and also look good on your applications. And also, I found it a lot of fun. I really enjoyed being able to do research as an undergrad. For the general public, I mean, if there's any museums or outreach events near you, your local university probably hosts events like we do that are just, you know, outreach, like, hey, come learn about space. There's a lot of really great web resources. The NASA website has some stuff for, you know, the general public. And
I steal a ton of stuff for this channel from just NASA, JPL, ESA.
yes, ESA is wonderful. One thing I really enjoy is NASA's APOD, Astronomy Picture of the Day. Every day they have a picture and an explanation, and that's a really great way to sort of, just do a little every day. And of course, there's a lot of documentaries and other good stuff out there. If you like astronomy, you can absolutely learn about astronomy and enjoy it without having to get real deep into the, volume integrals over a curved surface, which is just way too much. I think it's great to, learn about space. Obviously, it doesn't have the same impacts as cancer research all the time, but we're learning more about this vast and beautiful universe we live in. And I hope everybody has the opportunity to learn as much about it as possible.
Yeah. And don't sell yourself short. Astronomers and physicists have done amazing things indirectly. Like the internet was basically developed at CERN for scientists to talk to each other.
Every time someone presents like, well, CERN invented the internet. They're very proud of it.
Thank you so much for agreeing to be interviewed.
Space is wonderful. I love what I do, and I hope this has been interesting to watch, and I hope it spurs your interest further into all the wonderful things you can learn about outer space.
Thank you all so much for watching to the end. I hope you have a great day, and remember that science is a process. Astra out.
Bad Astra, to the stars, to the stars.
Whose perspective are we valuing as correct? If this was a question from the perspective of someone in the MAGA camp, it would probably be the James Webb Telescope, because they were living their best lives under a nearly fascist, well, mostly fascist regime. The majority is not necessarily correct. If I showed everyone in the United States a picture of like a very obscure plant, there would be a minority that can correctly identify it, and everybody else would just be wrong. It's more about feeling, and feeling sometimes can be facts. My facts are always my feelings. Another thing happens, another thing happens, another thing falls apart, another thing falls apart. Oh my god, there was another bad decision that he made. Oh my god, now there's a fucking riot. A lot happened in those 4 years that were more universally perceived than the building of the James Webb Telescope. So if we're going based on perception, we had to know that the Trump presidency was going on. We had no choice. We had no choice in experiencing all of the political hardships and divide as a result. Can there be a correct answer to this if it is based on feeling alone? I think I've dug myself into a philosophical hole. I'm just spiraling on this one.